What if the earliest light in the universe is not just a record of the past, but a message written in a language we are only beginning to recognize? That is the question a data scientist quietly confronted at a high-altitude observatory in the Chilean Andes, while doing what was supposed to be a routine calibration of the oldest light we can ever observe. At the Atacama Cosmology Telescope facility, far above sea level and far from human interference, the night shift is usually uneventful. The air is thin, cold, and still. Inside the control room, everything is controlled, minimal, and almost meditative, designed to isolate signals from the deepest parts of the universe. At around 4:14 a.m., local time on April 25, 2026, a scientist named Julian is running a standard noise reduction procedure on data collected from the cosmic microwave background, the faint afterglow of the early universe. This work is normally repetitive and predictable. He is essentially cleaning the data, removing interference from Earth, correcting instrument drift, and verifying that the telescope is accurately reading the uniform temperature of the universe as it appeared shortly after the Big Bang. In simple terms, he is making sure nothing is wrong with the lens through which humanity sees the earliest moment of existence. But as the final stage of the processing algorithm completes, something changes. On the screen, the expected random pattern of tiny temperature fluctuations does not behave randomly anymore. Instead, it begins to organize. At first, it looks like a glitch, something subtle enough to ignore. But within seconds, the structure becomes undeniable. A precise geometric pattern emerges, forming a perfect hexagonal arrangement embedded in the oldest light in the universe. Julian stops moving. This is not noise. It is not a software error, and it is not an artifact caused by the telescope. Every layer of filtering confirms the same thing. The pattern is real, and it is coming from the cosmic microwave background itself, the oldest observable structure in existence. He leans closer to the screen, trying to rationalize what he is seeing. The universe, according to everything we understand, should not produce structured geometry at this scale in its earliest light. The background radiation is supposed to be nearly uniform, with only tiny random variations left over from quantum fluctuations in the early universe. But what he is seeing is not random, it is organized, deliberate, almost mathematical in a way that feels unnatural. Then the analysis deepens. The pixel data reveals repeating numerical relationships that match a clean mathematical sequence. The spectral signature confirms that the pattern is not on top of the cosmic background, but embedded within it, as if it has always been there. Even more unsettling, the sequence aligns with the internal timing frequency of the telescope's own data capture system. That detail changes everything. If true, it means the instrument is not just observing the universe. The universe is, in some way, reflecting the instrument back at itself. Julian pushes his chair back abruptly, the wheels scraping against the floor. His breathing becomes shallow. What started as a calibration task now feels like a direct confrontation with something fundamental. He initiates a secure transmission to international astrophysics coordination channels, bypassing standard review protocols. This is no longer routine data. It is an anomaly that cannot wait for normal verification cycles. Because if this pattern is real, then it raises a question that no one is prepared to answer. Why would the oldest light in the universe contain a structure that mirrors human measurement systems? Why would the early cosmos encode a pattern that appears to anticipate the very tools used to observe it? At that moment, the assumption that the universe is a passive system begins to weaken. What Julian is seeing is not just a strange anomaly in data. It is a signal that challenges the idea of randomness at the foundation of existence. And as the telescope continues to collect information from the depths of time, it becomes clear that this is not a single irregularity. It is the beginning of a pattern that suggests something far deeper is embedded in the structure of reality itself. Something that does not just describe the universe. At first, the team tries to treat the anomaly as a technical issue, because that is always the safest explanation in a situation like this. Instruments drift, algorithms misread subtle interference, and even the cleanest systems can occasionally produce patterns that look meaningful when they are not. That is the default assumption in observational cosmology, and for good reason. The universe is noisy, and humans are very good at seeing order where none exists. But the data does not cooperate with that explanation. As Julian and the small group of on-call researchers begin a deeper verification cycle, they reprocess the same cosmic microwave background maps using independent pipelines. Different noise models, different filtering methods, different calibration assumptions. If this were an error, It should shift, weaken, or disappear under alternative processing. Instead, it strengthens. The hexagonal structure does not move. It does not distort. It appears consistently across independent reconstructions of the oldest light in the universe. That consistency removes the simplest explanation first. This is not a computational artifact. What remains is far more uncomfortable. The pattern is not random, and it is not local. It is embedded in the last scattering surface itself, the moment when the universe first became transparent, when photons began traveling freely through space after hundreds of thousands of years of opacity. In other words, this structure is not something that formed later. It appears to be written into the earliest observable layer of reality. The team begins to quantify it more carefully. Pixel density analysis reveals repeating mathematical relationships that resemble a structured sequence rather than stochastic variation. That alone would be unusual but not impossible. However, spectral decomposition introduces a second layer of concern. The pattern is not confined to one scale. It appears self-similar across multiple angular resolutions, as if it is preserved under zoom, like a fractal with a defined rule set. Then comes the third and most unsettling observation: the timing. The frequency of the detected pattern correlates with the internal clock cycle of the telescope's own data acquisition system. Not approximately, not loosely, but with a precision that forces statistical models into extreme improbability. The likelihood of such alignment arising from random cosmic fluctuations is effectively negligible under standard cosmological assumptions. This is the point where the interpretation shifts from anomaly to implication. If the pattern is not in the instrument, and not an artifact of processing, then it must originate from the signal itself. And if it originates from the signal itself, then the oldest light in the universe is carrying structured information that aligns with the technology used to observe it. That conclusion is not immediately accepted, because it feels like stepping outside the boundaries of conventional physics. But the data does not change just because the interpretation is uncomfortable. Julian escalates the alert. A secure channel is open to the International Astrophysics Union, bypassing standard peer review pathways. This is no longer an internal curiosity. It is now a potential foundational issue for cosmology itself. As the message is transmitted, the team remains focused on the live data feed. The hexagonal geometry persists, stable and coherent, sitting quietly within the microwave background like a hidden structure beneath the surface of reality. At this point, the conversation in the control room shifts. They are no longer asking whether the pattern is real. They are asking what it means for a universe that, according to standard models, began in a state of extreme simplicity and randomness. Because if complexity is present at the earliest observable moment, then either something fundamental about the early universe is missing from current theory, or the assumption that the early universe was purely random is incomplete. And that leads to a more uncomfortable possibility that no one says out loud yet. What if the universe did not begin in randomness at all? What if the earliest light is not just a remnant of creation, but a structured record of something that was already operating before what we call the beginning? The data does not provide an answer, but it clearly stops behaving like background noise. And as the team prepares for deeper analysis, one realization quietly settles in: they are no longer just studying the origin of the universe. They are studying something that appears to have left a signature inside it. What was there before everything began? Not before your life, not before Earth, not before stars or galaxies, but before space itself, before time had any meaning at all. It sounds like a simple question, almost childlike, yet it leads directly into one of the deepest limits of human knowledge. Because the moment you ask what came before, the beginning of everything, you are already using a concept that may not even apply. Before requires time. And if time itself had a beginning, then the word before may lose its meaning entirely. This is the kind of question that sits quietly at the edge of modern physics, where answers stop being certain and start becoming speculative. It is also a question that has followed generations of scientists, including those who have spent their entire lives studying the structure of the universe. The closer you get to that boundary, the more you realize something unsettling but fascinating. We may not even have the right language yet to fully ask what we are trying to understand. The standard picture we use today begins with what we call the Big Bang. According to our best observations, the universe is expanding. Galaxies are moving away from each other, not because they are flying through space from a single explosion point, but because space itself is stretching. This has been confirmed through multiple independent measurements, including the redshift distant galaxies, the cosmic microwave background radiation, and the large-scale structure of galaxies spread across the universe. Even distant supernovae have helped confirm that this expansion is not slowing down in any simple way. If we mentally reverse this expansion, running the cosmic film backward, everything in the universe moves closer together. Galaxies merge into dense clusters. Matter becomes hotter, more compressed, more extreme. Eventually, we reach a point where everything in the observable universe seems to converge into a single, incredibly hot and dense state. This is where the standard narrative places the beginning of everything. But when we push that idea to its limit, something important happens. The equations of general relativity, our best theory of gravity, begin to break down. They produce a condition known as a singularity, a point where density and temperature become infinite. In mathematics, this signals something very specific. Not necessarily that nature contains infinities, but that our model has reached the edge of where it can reliably describe reality. And that distinction is crucial. A singularity is not necessarily a physical object or event. It is a warning sign from the theory itself, telling us that we are applying it beyond its domain. In other words, the beginning described by this singularity is not confirmed reality. It is a boundary of understanding. This is where modern cosmology becomes less certain and far more interesting. The Big Bang, as commonly described, is not necessarily the absolute origin of everything. It is the point where our current physics stops working clearly. What lies beyond it is still an open question. To move further, we need a deeper theory that unifies gravity with quantum mechanics, something we do not yet fully have. So already, the simple idea of a beginning becomes less solid than it first appears. The universe may not have started in the way we imagine at all. Instead, what we call the Big Bang may be more like a transition point, a boundary between different physical regimes, rather than a literal first moment of existence. And once you accept that possibility, the question of what came before does not disappear. It becomes even more important. It just becomes harder to answer with confidence. What follows from this uncertainty is one of the most important developments in modern cosmology. The idea that the Big Bang may not have been the absolute beginning, but instead a transition from an earlier state of reality that we do not yet fully understand. In this view, what we call the beginning is actually the limit of our current theories, not the limit of existence itself. One of the leading frameworks that pushes this idea further is inflation theory. It suggests that in the earliest fraction of a second, the universe did not simply expand in a slow, steady way. Instead, it underwent an extremely rapid phase of expansion, driven by a high-energy quantum field often called the inflaton. During this moment, space itself expanded at an extraordinary rate, stretching tiny regions far beyond what we can observe today. This idea helps explain several otherwise puzzling features of the universe. For example, the cosmic microwave background radiation, which is the faint afterglow of the early universe, appears almost perfectly uniform in all directions. Without inflation, distant regions of space should never have been in contact long enough to reach the same temperature. Inflation provides a mechanism for that uniformity by suggesting that everything we see was once part of a much smaller, connected region before being stretched apart. It also helps explain why the universe appears so geometrically flat on large scales and why certain predicted exotic particles are not observed. In this sense, inflation is not just an abstract idea. It is a framework that makes the universe we observe easier to understand. But inflation introduces something even more unexpected. In many versions of the theory, inflation does not stop everywhere at once. Instead, it continues in some regions of space while ending in others. This leads to a picture of reality known as eternal inflation. In this scenario, new bubble universes are constantly forming. Each bubble can have its own physical properties, its own version of the Big Bang, its own history of expansion and structure. Our observable universe would then be just one such bubble, a local region where inflation ended and normal cosmic evolution began. Meanwhile, beyond what we can ever observe, other regions may still be inflating or forming entirely separate universes. If this picture is correct, then the question of what came before our Big Bang becomes more layered. It may not be a single answer. It could be another phase of inflation, a different vacuum state, or a quantum fluctuation in a deeper underlying field. The honest position of modern physics is that we do not yet know which, if any, of these possibilities is correct. What we do know is that the Big Bang, as we typically imagine it, is likely not the ultimate starting point of everything. It is more accurately described as the beginning of our local observable region, the moment when our particular cosmic environment transitioned into its current form. But whether time itself began there, or whether it extends in some form beyond it, remains an open question. This is where cosmology becomes more than just a study of distant space. It becomes a study of limits, of how far human understanding can reach when pushed against the structure of reality itself. And at that boundary, the line between physics and philosophy begins to blur in a way that is unavoidable. Because once you accept that the universe may not have a single simple beginning, you are forced to rethink what a beginning actually means in the first place. Once we step beyond the idea of a single, clean beginning, the question of what came before stops being a simple, missing piece in a timeline and becomes something far more fundamental. It becomes a question about whether time itself is a basic feature of reality, or something that emerges from deeper physical processes we are only beginning to understand. In standard general relativity, if you run the equations all the way back to the Big Bang, time appears to shrink down toward a singular point. In that simplified picture, asking what happened before the Big Bang is like asking what lies north of the North Pole. The language breaks down because the coordinate system itself ends. If time truly began at that boundary, then before has no physical meaning. But this clean picture depends on pushing a classical theory to an extreme where it is no longer reliable. General relativity does not include quantum effects, and at extremely small scales and extreme energies, quantum mechanics becomes essential. When we try to combine these two frameworks into a single theory of quantum gravity, the nature of time itself becomes much less clear. In some modern approaches, time may not be fundamental at all. Instead, it could emerge from more basic quantum relationships, the same way temperature emerges from the motion of particles, even though no single particle has a temperature on its own. In that sense, time might be a large-scale statistical effect rather than something built into the deepest level of reality. If that is true, then the Big Bang is not necessarily the start of time, but a transition in which time as we experience it begins to take shape. Before that transition, the universe may have existed in a state where the distinction between past and future was not well defined in the way we understand it. This leads to one of the most striking possibilities in modern quantum cosmology, that there may not have been a sharp beginning at all. Instead of a single initial moment, the universe could have passed smoothly from a quantum state with no classical time into one where time becomes meaningful. In that picture, the origin of time is not an event inside time, but the emergence of time itself. This changes the way we think about causality as well. Cause and effect depend on a clear direction of time. If time is not fundamental at early stages of the universe, then the usual idea of what caused the Big Bang may not apply in any straightforward way. The question itself may be asking for a structure that does not yet exist in that regime of physics. What makes this even more fascinating is that similar ideas appear when we look at our best attempts to describe the universe at the quantum level. Some models suggest that the earliest state of the universe could be described without a preferred time direction at all, with the arrow of time emerging only as the universe evolves into more complex structures. In that sense, the Big Bang may not represent a sharp boundary in reality, but a kind of phase transition, where a timeless or nearly timeless quantum state gives rise to the flowing time we experience. Not a first moment, but the beginning of a new way of organizing existence. And once that possibility enters the picture, the question, what came before, stops being a question with a missing answer and becomes a question about whether before was ever a valid concept to begin with. Once we reach this point in the discussion, something subtle but important becomes clear. The question of what came before the Big Bang may not be a question with a single missing answer, but a sign that our intuition about time itself is incomplete. The language we naturally use before, after, beginning, end, comes from everyday experience inside a universe where time flows in a consistent direction. But at the deepest level of physics, that structure may not be as fundamental as it feels. If time is emergent, as many approaches to quantum cosmology suggest, then the early universe is not a place where time suddenly turns on like a switch. Instead, it is more like a gradual formation of order from a deeper underlying quantum state. In that case, the Big Bang is not the start of everything, but the point where time becomes a meaningful concept within the evolution of that system. This idea forces us to rethink what we even mean by an origin. In classical thinking, origins are simple. Something exists, and at some earlier moment it did not. But if the structure of time itself is part of what is forming, then there may be no external viewpoint from which to describe a true first moment. The universe does not begin in time. Rather, time is part of what the universe is doing. In more speculative models of quantum cosmology, the universe may transition smoothly from a state where classical time has no definition into a state where a clear arrow of time emerges. In that sense, the Big Bang is better understood as a boundary of description rather than a boundary of existence. It marks the point where our current physical language becomes effective, not necessarily the point where reality itself started. This also reframes how we interpret cosmic history. The further we push toward the earliest moments, the more we realize that what we call initial conditions may themselves be the result of deeper processes. Inflation, quantum fluctuations, vacuum states, and potential multiverse structures all suggest that the universe we observe could be one local expression of a much larger and more complex framework. From this perspective, asking what came before the Big Bang may be similar to asking what lies beneath the foundation of a structure when the foundation itself is part of the building process. At some level, the question may not have a single answer because it assumes a separation between time and existence that may not actually be there. And yet, even if physics pushes us toward these abstract and sometimes counterintuitive ideas, the question itself remains deeply human. It reflects a desire to understand not just how the universe behaves, but where it comes from in the most fundamental sense. That desire does not disappear even when the answers become more complex. If anything, it becomes stronger. What modern cosmology offers is not a final answer, but a shift in perspective. The Big Bang may not be the absolute beginning of everything, but it is the beginning of what we can currently describe. Beyond it may lie deeper layers of physics, or entirely different structures of reality, or concepts we do not yet have the language to express. So we are left in a careful, honest position. We do not know what came before the Big Bang, and we are not even certain that before is the right word. But we do know that the universe, as we observe it, is richer, stranger, and more layered than a simple origin story suggests. And that realization, in itself, is one of the most important insights modern science has given us. The beginning, it turns out, may not be a point at all, but a doorway into something far larger than we can yet see.